Okay, so welcome everyone to the third talk of the IARCS verification seminar series. So this series is planned to be a monthly seminar series, roughly the first Tuesday of every month. So the advertisements for these talks will be sent out in the SM India mailing list, as well as in the VSS mailing list. So if you want to subscribe, please visit the web page for the talk. I will post it on the chat. Okay. So now coming to today's speaker. So it gives me great pleasure to welcome Suguman Bansal to today's talk. She's a postdoctoral fellow at University of Pennsylvania, mentored by Rajiv Alur. She completed her PhD from Rice University, advised by Moshe Wadi. Prior to that, she did her undergraduate studies at Chennai Mathematical Institute. So her research goal is to design, develop, deploy safe AI systems using formal methods and programming languages. So she has worked on several subjects, including formal methods for reinforcement learning, automata-based quantitative reasoning, and reactive synthesis from high-level specifications. So today she will talk about reactive synthesis from quantitative constraints and automata approach. So looking forward to the talk. Suguman, over to you.
Thank you, Srivatsan. Thank you for the invitation to speak at the verification seminar series, and thank you all for attending virtually. Today's talk is about reactive synthesis from quantitative constraints. Now, the mention of quantitative constraints might conjure up images of algorithms that require complex techniques like numerical methods-based techniques like optimization, linear programming, and so on. Today's talk, I will introduce a new approach which requires only and only automata-based methods. So it is a paradigm shift from what is traditionally known. So let's start rather broadly. Yeah, let's start broadly. Formal methods, as we all know, is the method of obtaining rigorous mathematical guarantees on the correctness of computational systems. And in the past couple of decades, we have seen wide-scale adoption of formal methods in verification and synthesis of hardware and software systems, so much so that industrial labs industrial development of software and hardware have really started adopting these techniques. But as we are in the AI boom, artificial intelligence boom, a whole new generation of computational systems have been introduced. And these computational systems are intelligent, meaning that they have the ability to interact with an external and uncontrollable environment. So we could have a domestic purpose cleaning robot that interacts with its surroundings in order to avoid collisions with either fixed or moving obstacles. We could have smart IoT devices, such as a smart thermostat that interacts with a temperature sensor, an AC, a heater, in order to maintain ambient temperature, and so on and so forth. So as complex as these systems may seem, in reality, they are really a reactive system, which is one that a reactive system interacts with an uncontrollable external environment. In each step of the interaction, the reactive system receives an input from the environment. Based on the input, it generates an output which goes back into the environment. And this sequence of interaction continues until the reactive system is able to achieve its objective. Now, as you may have guessed, design and development of reactive systems is very hard. One expects these systems to be safe, reliable, and trustworthy. But currently, the state of reactive systems in terms of correctness is not one that we can boast of. So here is this is a robot from Boston Dynamics. It's a domestic purpose robot. And there is this really funny video on YouTube in which this robot tries to hand over a can of Coke to a human. And when the human grabs the can of Coke, the robot gets so confused that it begins attacking the human. This by no means is safe or reliable behavior. Other failures of reactive systems are much more catastrophic. And as highlighted in this post-mortem report, the problem with designing reactive systems is that it is hard to predict all possible situations that would happen in the wild. Meaning, from the system designer's perspective, it is very difficult to predict all possible situations in which the environment could behave, and even harder to design correct responses to every situation. Now, this is the opportunity for formal methods research. A lot of times for these systems, it has been observed that specifying the intent, the desired behavior of these systems is easier. So the question is, can we automatically generate a correct reactor system from a high-level specification? That is the problem of reactor synthesis. Given a high-level specification, can we design a correct by construction reactor system? That's what today's talk is going to be about. In today's talk, I'll start with a brief overview of the existing work on reactor synthesis. Most existing work uses...
I have a question here. Yeah, question. So you just started by saying the environment is uncontrollable, but then you say that you can specify it, okay? And so how can you specify what the behavior should be? So the specification of how the reactor system should behave for an unpredictable environment itself is a complicated thing, no?
Right. So the specification, I mean, that's a great question, because so the specification is not about the environment. The specification is simply about the task of the system. So the task of the system could be something as simple as saying, from my current position, navigate to a given destination. The task could be as simple as that.
That's okay. So, but that's not a complete specification. So you are assuming some specification and deriving the synthesis. So you're not attacking the problem of specification. Okay, so that's fine.
Right. So in this talk, we'll assume that the specifications can be given, and how easy it is to write specifications is a whole conversation in itself. But at least what we know is that specifying specifications is easier than writing the system from scratch.
Yeah, but that problem of reactive synthesis, that's not a new problem. You know, that has been studied quite extensively.
Correct.
Okay.
That's right. Right. So I will start with an introduction of the existing work in reactor synthesis, right? So that will be the first half of this talk. So I'm not claiming that reactor synthesis is a new problem. It has been studied extensively.
No, I know. I got confused because you started with AI safety. So I thought that AI safety means, environment, we're talking about synthesis in the context of unknown environment, but that's not the problem that you are, at least in the first part, describing. Am I correct?
Yes, the environment is not unknown, it is uncontrollable.
Oh.
If the environment is unknown, then actually synthesis techniques don't work. In those cases, we need learning-based techniques. Right, so that is a crucial distinction. The environment is uncontrollable, meaning it is unpredictable, but it is known. So a model of the environment is given, and a high-level specification is given. Yes. All right. Thank you for the clarification question. So I will start with an overview of reactor synthesis. And most existing work on reactor synthesis has actually looked at specifications which are qualitative by nature. But as AI systems become more complex, there is a requirement to be able to specify much more nuanced, much more richer specifications. And which is why in the rest of the talk, in the bulk of the talk, I will discuss my work on reactor synthesis with quantitative properties. And with quantitative properties, you can specify behaviors which are much more richer than what can be done with qualitative specifications. All right. So let's get started. Let's look at this really simple example. We are given a grid with two agents, a robot and an adversary. Both of these agents can move. And now suppose the robot's task is to reach a given destination on the grid. Now, if the adversary was not present, then the specification could have easily been, then we could have easily satisfied the specification, because all we would have to do is search for one path that reaches the destination from the current state of the robot. But in the presence of an adversary, that is not possible because the adversary could block a single path. So in these cases, we need to generate a strategy. So that no matter where the adversary is located, the robot can still reach its destination. So the strategy in this case is the reactive system, which can respond to the current location of the adversary and decide how to navigate around it to reach the destination. Now, this problem can be formalized, can be modeled as a game between the robot and the adversary. This diagram is just for illustrative purposes, but what this diagram shows is that this game is played between two players, a system player, the robot, and the environment player, the adversary. The rules of this game are really simple. The first rule is that the game begins in the initial state. In this case, the initial state is V0, indicated by the tiny arrow on the side. The second rule is that from the square states, the system player chooses which state to go to next. And the third rule is that from the circle states, the environment player will choose which state to go to next. And now the system will win this game if it is able to satisfy its specification. Meaning, if it is able to generate a strategy so that every possible execution using that strategy can satisfy the spec. In this case, suppose the specification is something simple, which says reach a given state V3. Then let's look at what possible strategies there could be. Right? So suppose the system decides to choose to go to state V1 from the state V1, to go to state V1 from the state V0. Now, this strategy will not satisfy the specification because, as you can see, if the environment chooses to remain in V1 forever, the specification will not be satisfied. So this choice of strategy is not a correct strategy. The strategy does not satisfy the spec. But if we take another strategy, in which case from V0, the system chooses to go to V2. In this case, from V2, the environment has no other option but to go to V3. So under this strategy, where the system chooses to go to V2 from V0, the specification is satisfied under every possible behavior of the environment player. And this strategy is indeed a winning strategy for the system. Now, reactive synthesis is the problem to automatically construct such a strategy. So given a specification, and in existing work, the specification is a qualitative specification. So it could be specifications like reachability objectives that say to go to a certain state, safety objectives, which say to avoid a given set of states, or something much more complex, expressed using regular expressions, linear temporal logic, and so on and so forth. So given a qualitative specification and a model of the system and environment interaction, the reactive synthesis problem is to generate a strategy F. And the strategy F is a function from sequences paths on the graph to a new vertex. Here, V are the vertices, the states in the graph, and Vs are the square states. So Vs are the states from which the system chooses which state to go to next. So a strategy is a function from a history of executions to a new state, which instructs the system on which state to choose next, such that every execution of the strategy satisfies the specification. Now, reactive synthesis is in fact a very well understood problem. The problem first dates back to Church's problem in the 1950s. And since then, initial works were focused on the theoretical foundations, which are based on automata techniques. And once the theoretical foundations were well developed, more recent work has focused on designing tools and algorithms which are scalable and efficient and their applications. I've given a representative set of some of the recent works. This is not it's not an exhaustive list by any means, but this is just to show the amount of work that has been done in reactive synthesis from qualitative specifications. Right? But now qualitative specifications are not sufficient to encode all the kinds of behaviors. And so there is a need to perform reactive synthesis from much more richer, much more nuanced specifications. And in this talk, I will discuss my work on reactive synthesis from quantitative specs. So let's start with a simple motivating example of why we need richer specifications. So this is the same game. It's the same robot. It's the same grid with a robot and an adversary, both of which can move around. Now, suppose the robot's task is to reach a destination, but the robot also wants to maintain a distance from the adversary. Now, this would be important because perhaps the grid is such that it's actually not possible for the robot to always avoid the adversary. So in these cases, we may instead want to say that overall, the distance that the robot maintains from the adversary should be high. There could be places where the distance is small, but in general, we want the distance to be large, and the larger the distance, the better it is. Now, these kinds of specifications, these maintain distance kinds of specifications, which is giving a high positive reward if the distance maintained is high, and a small reward, a negative reward if the distance maintained is small, are very difficult to express using qualitative specifications. Instead, which is why we want to use quantitative specifications, where it is very natural to talk about things like distances, right? And now the question becomes, given that the specification is a combination of quantitative and qualitative specifications, can we generate a strategy which will satisfy the spec, right? Now, so just another point I want to mention here is that quantitative specifications in this case refer to rewards with respect to distance, but you can also imagine quantitative specifications in order to talk about resource consumption. So we might want to say that every step, every interaction in this grid costs a certain amount of battery life, and we want to ensure that the robot never runs out of battery, and so on and so forth. So there are a lot of behaviors, desirable behaviors that quantitative specifications could encode much more naturally than qualitative specifications. So even problems like this, where we combine quantitative and qualitative specifications, can be modeled as a game. The only difference now, and this is again the same kind of graph game between the system and the environment player, the only difference is that now on every edge, there is a cost. And this cost refers to the quantitative cost of executing each action in the actual space, right? So now every execution in this game is also associated with a unique sequence of costs. And therefore, that is what we use to compute the cost of an execution. So suppose the weight sequence of a given execution is A, then the cost is given by the discounted sum, where for a given weight sequence A, discount factor D, which is greater than 1, the discount factor is simply the sum of diminishing returns. So it is A0 plus A1 by D plus A2 by D squared, and so on and so forth. The reason discounted sum is used in these, the discounted sum is used to compute the cost of executions is because over infinite length weight sequences, this is one of the aggregation functions which is guaranteed to converge. Other functions like limit average do not have convergence guarantees, which is why discounted sum is usually discounted sum finds applications in planning and synthesis, reinforcement learning, and so on and so forth. Now, in this case, given such a game, the specification is a combination of a qualitative goal and a quantitative goal. The qualitative goal is as earlier. It could be a reachability objective, safety objective, LTL, regular expression, and so on and so forth. The quantitative goal in our case are called satisficing goals. And what the satisficing goal says is, given a threshold value T, can you ensure that the cost of every execution exceeds the threshold? And then the synthesis problem is, again, given a game and a specification, the specification combines quantitative and qualitative goals. Can we generate a strategy such that the strategy satisfies both of the goal, both the quantitative and the qualitative constraint at the same time on all executions? So let's look at a simple example again. Here I have a simpler game, just a two-state game. As earlier, system chooses from the square states, environment chooses from the circle states. Suppose the qualitative goal of the system is to visit the state V1. And suppose the system's quantitative goal, the satisficing goal, is to ensure that the threshold, that every execution exceeds a threshold value of half. Then now let's look at one candidate of what a strategy could be. And suppose the strategy that the system adopts is to choose to go to V1 from the state V0. Now this strategy doesn't work, but because although this strategy satisfies the qualitative goal of visiting state V1, it does not satisfy the satisficing goal. As you can see, if it follows a strategy, if it follows the given strategy, then in case the environment chooses to remain in V1, the resulting weight sequence will be the weight sequence 0 followed by -1s forever. And the cost of that sequence would certainly be less than half. So this strategy does not satisfy both the specifications simultaneously. What about another strategy? Suppose the strategy is to remain in V0 forever, which is that the system chooses to remain in state V0. Now, while this strategy ensures that the satisficing goal is satisfied, because in every step, it will receive a reward of 1, it does not satisfy the qualitative goal, which is to reach the state V1. But suppose you take another strategy, which is to remain in V0 for a number of times, for some number of times, and then move to V1. Then we can see that depending on what the discount factor is, the system can choose to remain in V0 for a sufficient number of times. By doing that, it can ensure that the total cost will exceed half. And then finally, it can move to V1, from where it can ensure that even the qualitative goal is satisfied. So what I want to illustrate is that combining qualitative and quantitative specifications means that the nature of the strategy that needs to be generated can become a little bit more complex. And several works in the past have attempted to solve this problem. However, none of the existing solutions are sound. So if none of the existing solutions are sound, what that means is that if existing solutions generate a strategy, it is possible that the strategy may not satisfy both the quantitative and the qualitative specifications simultaneously. At a high level, the reason this happens is because qualitative goals, as I mentioned earlier, are solved using automata-based methods. Satisficing goals, however, in existing work has been solved using optimization-based methods, numerical methods. In reality, what they are doing is that they're solving a min-max game between the system and the environment player, and that requires optimization-based methods to use. That requires optimization-based algorithms. The problem here is that automata-based methods and optimization methods are so different that their combination is actually not seamless. And it is when existing works have tried to combine both of these techniques that the soundness guarantee fails. So the question we ask is, can we design alternatives to this optimization-based method? More specifically, can we design automata-based methods in order to solve satisficing goals with the hope that these automata-based methods will combine well with the automata methods for qualitative goals, and thus giving a sound algorithm for reactive synthesis from quantitative and qualitative goals, right? And that's where, this is where our work on comparators is really an automata-based technique to perform quantitative reasoning. The real idea behind comparators is that it takes a problem in quantitative reasoning and reduces it to a problem in qualitative reasoning. In this talk, we will look at how it is used in the context of reactive synthesis, but in other works, we have shown that comparators have benefits even in quantitative verification, and it could have potential benefits in reinforcement learning with formal guarantees and even precise arithmetic. So let's dive into details. So let's now dive into the details. But this would be a good point to stop for questions, if there are any. All right.
Can I ask a question, Suguman?
Please.
Hi. So when you say qualitative goals, what is the scope of qualitative goals? Any omega regular objective or just safety properties or what?
Qualitative goals means any omega regular objective.
Okay.
Yeah.
Yeah, that combining that with optimization is, yes, you have to work harder. Yes.
You need to work harder, but if you want to get formal guarantees, existing work has not been able to combine the two.
Okay.
So, Suguman, Deepak here. I just wanted to ask a question on this satisficing property. You need to expend a certain amount of resources, right? I mean, a minimum amount. Why is it phrased that way? I mean, you were talking about conserving resources while meeting the qualitative objective.
So what I meant was, I was giving another example of what a quantitative objective could be. And the example was to say that suppose we also take into consideration the amount of resource spent in each step of the interaction. Then the objective there might be something different. And the objective might be that we need to ensure that at every step, the existing battery life is greater than 0. Right? So satisficing goal is one example of a quantitative objective. There could be many more. There could be many more. Yeah.
Okay, makes sense.
Yeah. All right. All right. So let's dive into the meat of this talk. And just so that we are all on the same page, I'll introduce what a Buki automata is. A Buki automata is simply.
If I ask one question about that, there's a follow-up to Deepak's thing. So satisficing goal. His thing was, why are you doing something greater? Okay, so we use. It was not clear, your answer. So you could have satisfying goal, the quantitative goal, to be as complex as, say, some linear constraints have to be satisfied. Those kinds of things are also possible quantitative goals, or some number has to be something greater or less or something like that.
Right. So in general, quantitative goals could be much, much more complex. But in the scope of this talk, we are saying that the cost within the scope of this talk, we're just talking about discounted sum of executions being greater than a fixed value. So it could be lesser than a fixed value. We don't really care about whether it's greater to, less than, equal to, whatever. For sake of simplicity, I just said it should exceed a given threshold value.
Okay, so you're limiting yourself to those kinds of constraints.
Yeah. So in our case, the quantitative constraints are limited by satisfying goals. Yeah. But the point with satisfying is that a lot of times when these constraints, when people talk about quantitative constraints, they'll usually try to find the optimal solution, right? So in some ways, you can say that satisfying is saying that optimal solutions are not really required. Instead, it would be sufficient to look for good enough solutions, right? So it is an alternative to optimization. And actually, you can even see through this example that there is no optimal solution with respect to the discounted sum, which will satisfy the qualitative constraint, because the optimal solution is to remain in V0 forever, and that will just not satisfy the qualitative goal. So that is also a limitation with optimizing the costs. So satisfying sort of relaxes the quantitative goal a bit, and that relaxation is what can lead to even realizing specifications that combine quantitative and qualitative goals. Right?
Yeah.
All right. Okay, so what is a Buki automata? And this is just a refresher. A Buki automata is an automata that accepts words of infinite length. So it has finitely many states defined over a finite number of alphabets. Some states are accepting states. In this diagram, the accepting states are indicated by double circles. And the transitions between these states are on the alphabets. Now, a run in this automata is accepting if the run visits an accepting state infinitely often, and the word is said to be accepting if it has an accepting run. Now, a Buki automata is deterministic if from every transition there is at most from every state there is at most one transition to a different state on any alphabet, and otherwise it is non-deterministic. So in this diagram here, the automata is non-deterministic because from S0 on the alphabet A, there are two transitions out of it, right? Now, why do we care about automata? And here is why. Well, I claim that comparison is the fundamental operation in quantitative reasoning. For example, in the satisficing goal, all we require is that the cost of an execution should exceed a fixed value. So all I'm really asking is, given a weight sequence, is the cost of that weight sequence greater than a fixed value? And more generally, one could sort of just ask that, given any two weight sequences, is the cost of one weight sequence greater than the cost of another weight sequence? And all of quantitative reasoning, if you really trickle it down to what the fundamental operation is, it will be one of these two, either comparison to a fixed value or comparison to another sequence. Now, comparison is also hard because weight sequences are infinite in length. So if the weight sequences are infinite at length, it might not be possible to compute the actual value, to compute the cost of these sequences. So the question really is, if we cannot compute the cost of weight sequences, how do we perform comparison? And more specifically, the question we ask is, can we perform this comparison, possibly without computing the actual costs, using automata? And our idea is that, well, you can think of every weight sequence as a word of infinite length, right? So if the weight sequences are bounded by this value mu, then the finite alphabet, and suppose these are integer weight sequences, then the finite alphabet over which weight sequences are defined is simply minus mu to mu. So can we use this insight that weight sequences are nothing but infinite words to somehow compare their cost? So that's what a comparator is. So given a discount factor D, an equality or an inequality relation R, and an upper bound mu, A and B are simply weight sequences over sigma omega, where sigma are the integers from minus mu to mu. I want to define something. I want to define a comparator that will accept the tuple of sequences A comma B if and only if the discounted sum of A relates to the discounted sum of B with respect to the relation R. Right now, why is this heading towards compare without compute? Because if the word A comma B is accepted by this comparator, then we know that A is greater than B, and if not, we know that A is not greater than B. So this, if we can construct a comparator, if we can construct an automata for this language, then we would have reduced the problem of comparison to the problem of membership in an automata. So the real question is the comparator an automata? So let's start with a simple case of when the discount factor is an integer, right? So the first intuition we have is that the discounted sum of a sequence can really be thought of as a number in a given base D. So if my sequence capital A is the sequence A0, A1, A2, and so on, the number the discounted sum generates is the number A0, decimal point, A1, A2, A3, and so on. So given this, the question of comparison becomes to compare the value of two numbers in the number system with base D. Now usually we can compare two numbers in a given base by performing a lexicographic comparison, right? The only kinds of outliers to this would be the numbers like 0.999 and 1.000, right? But that is still the only kind of outlier. So maybe lexicographic reasoning plus outlier management would work out. But there is still one more caveat here. And the caveat is that the values AI are bounded by mu. They are not bounded by D. So AIs could be greater than equal to D. Furthermore, these AIs could be negative. So this lexicographic reasoning with outlier management will not work. But we are still in this very distorted sort of number system. But what we can still do in this number system are things like addition and subtraction. So if we are interested in knowing whether A is less than equal to B, we could try to construct another number C, which is the difference of B and D, and ensure that the difference between these two numbers is greater than equal to 0. If we have done that, we have ensured that the discounted sum of A is less than equal to that of B. But there is still one problem here. Normally, when we think of addition or subtraction, we think of numbers of finite length. In our case, these B's and D's are of infinite length. So how do we perform addition and subtraction over numbers of infinite length? Right? How do we compute the difference of these two numbers? But I claim it can still be done. And here's why. Let's recall how we performed addition and subtraction of numbers in a regular number-based system. So suppose I work with the base D equal to 10, so the discount factor is 10. Then the way we perform it, now suppose I'm given two numbers, A and C, right? And observe that A and C, I am allowing the digits to be greater than the discount factor. But we can still use basic high school arithmetic to find the sum of A and C to find B. The way we would do it is we would start with the least significant digit, right? Take the sum of the values in A and C. The sum would be 12. So what we do is that we remove the carry value 1 to the next column, retain the 2 in the current column. We can do the same for the next sequence, and we can keep doing that until we reach the final sequence, where we simply take the sum of the carry value A and C and write that as the sum in the sequence for B. So this is basic high school arithmetic. You start with the least significant digit, calculate the sum of columns, keep pushing the carry value forward. At the final column, just take the sum of everything. Our case is slightly different. In our case, the sequences are of infinite length. And because the sequences are of infinite length, there is no less significant digit. There is no least significant digit. All we can do is we can begin from the most significant digit, and somehow from the most significant digit, we want to be able to compute this different sequence C. But I claim that we can still use the same two equations, the yellow and the pink equation, in order to compute C. But we will do that with a touch of non-determinism. So the idea is that at every step, we want to guess a candidate value for C and check immediately if that is correct. And these two equations, the yellow and the pink equation, will help us in doing that. So here's what we'll do. In the first column, at the most significant column, we will guess a candidate value for C and a candidate value for X. And we will check whether these candidates are correct using the yellow equation. Once that is done, we will use the pink equation to check candidate values for the next column, and so on and so forth. And I claim that if A is less than equal to B, then there must be a sequence C that can be generated using this guess and check procedure. And in fact, to finally ensure that C is greater than equal to 0, all we need to do is that while guessing digits in the sequence C, let's just guess values which are non-negative. And if we do that, we are guaranteed that the discounted sum of C will be greater than equal to 0, and thus discounted sum of A will be less than equal to that of discounted sum of B. Now, how do we capture these ideas into an automata construction? And this is how we do it. I'll say that the states of my automata are going to be all combinations of X and C's, all combinations of Xi's and Ci's. From the start state, transitions will have to follow the yellow equation. And from every other state, transitions will have to follow the pink equation. So if I can construct an automata that has transitions as follows, I will be guaranteed that any sequence A, B, which is satisfied by this automata, will be such that discounted sum of A is less than or equal to that of B. So the only question is whether there are finitely many such values of xi's and ci's. So for ci's, as I already said, we are guessing what the difference of two sequences. We are guessing the values of ci's. So because we know that if the difference is non-zero, that number must be representable by using the digits 0 to d minus 1. So all the guesses for ci's can be limited to be non-negative numbers between 0 and d minus 1. For xi's, really the xi's are these bounded values, are the carry values with some amount of look ahead. So even there we can show that the xi's are bounded. But there is one issue, that these xi's could be non-integers. Turns out when the discount factor is an integer, the xi's are also integers. To see why this is true, if we observe the pink equation, then we can see that when A, C, and B's are all integers, then the xi's can also be forced to be integers. So when the discount factor is an integer, the xi's can be forced to be integers, and therefore there are only finitely many cases for xi's and ci's. And in this case, the automata will have finitely many states. However, when the discount factor is not an integer, if we eyeball the pink equation a little bit more, we can see that xi's can actually become arbitrarily small. And in fact, they will not just be integers. And in this case, there may not be finitely many values for the xi's. So what we summarize from here is that when the discount factor is an integer, then using arithmetic plus non-determinism, we can generate a non-deterministic Buchey automata for the comparator. However, when the discount factor is not an integer, then we can prove that the comparator cannot be an automata. And the reason it cannot be an automata is because the carry values can become arbitrarily small, and therefore there would be infinitely many states. But there is still, and just talking about the number of states in the comparator, then for integer discount factors, if the upper bound is mu, then the comparator is fairly compact. It simply has order mu square number of states in all, right? And it is a non-deterministic Buchey automata. But can we do something about the non-integer discount factors in order to get a comparator which is a Buchey automata? And for that, what we do is we use approximations. So we claim that, so the way we define an approximate comparator is that when the discount factor is not an integer, then we can take an approximation factor of our choice, a small approximation factor. We say that the comparator automaton will accept, if it accepts a sequence A, B, then the discounted sum of one would be greater than the other. But if it rejects, then it is going to reject it with some approximation error. So here the error is going to be d epsilon. And because the epsilon is really a user provided input, it can be made as small as one wants. And what we can show is that one can construct approximate comparators and ensure that those are non-deterministic Buchey automatas. And the idea is that the problem earlier was that the resolution values, the carry values could become arbitrarily small. So what we do is that we assign a resolution to the carry value. So what we do is that we say that every carry value will be rounded up to a resolution value, right? And this resolution could be a small number governed by the discount factor and the approximation factor. And then once we do that, we can show that because it prevents the carry values to become arbitrarily small, there will be finitely many such values. And then we can try to reconstruct the comparators as we did earlier in order to obtain a non-deterministic Buchey automata. And there are some assumptions under which this happens, but these assumptions are on the resolution value, so they are non-restrictive assumptions.
May I ask a question at this point?
Please go ahead.
This Paritosh. So, maybe I missed something very simple, but I can imagine that, when you are checking whether one, discounted sum sequence A and B, whether the discounted sum of one sequence A is larger than B, as you go farther, of course, the values, precision falls off so sharply, at some point non-deterministic. But when you are doing equality of two sequences, I'm a little worried, two formal power series may converge to the same value, but they may oscillate and converge in a very complicated way, even if D is a rational. So or is there a very simple argument which I missed?
So your question is, it might work out for greater than, it might work out for less than, but will it work out for equality?
Yeah.
Right? So if you want to think of it in terms of automata, then the way you can think of it is that, well, Buki automata are closed under all operations, right?
Mm-hmm.
All set theoretic operations.
Mm-hmm.
So if I have a comparator for, so let's actually go back to the exact comparator, right? So we're talking about exact comparators here, integer discount factors.
Okay.
So if the comparator for one relation is a non-deterministic Buki automata, I claim the comparator for every relation is a non-deterministic Buki automata. And that is because NBAs are closed under all possible.
No. But then my question is distinguishing between greater than and greater than equal to.
Right. So to distinguish between the two, what we would do, we would change the acceptance condition.
Mm-hmm.
If we want to ensure strict greater than,
mm-hmm.
then while guessing the sequence C, what we want to ensure is that at some point, we guess a non-zero value. And that is sufficient to guarantee strict greater than. If all we want is greater than equal to, it is sufficient to say I want non-negative guesses. So that difference that is the difference between greater to and greater than equal to.
Okay. Yeah. I have to read up. I'm not, but I will believe you, and let's go ahead. Yeah. Interesting property. Yeah.
So Suguman, just a question while we are on that slide. So, I mean, so when we are normally, comparing, or let's say just adding up to decimal numbers, we go from most significant to least significant, right?
We normally these are finite, so we start with the least significant.
Sorry, we start with least to most, right? Sorry, right. But here we are reading from most to least, right?
Correct.
So how do you how are you handling that?
So the idea is that any guess for the values of xi's and ci's which satisfy these equations will be a correct guess. That is a property we prove. That if at every stage, I guess the xi, ci using these equations at the bottom, then I can ensure that discounted sum of A plus that of C is equal to B. I mean, you should think of it as, okay, what is the challenge behind this guess? The challenge behind the guess is that I don't know how large the carry value should be, right? And if suppose by accident, I had guessed that the carry value X would be some large number, say 20, then as long as I can adjust the value of C so that the C is still a reasonable number, that much is enough. So that is the magic behind this.
Okay, so the carry is somehow, you have to verify that the carry that you've guessed is
correct.
Okay, and that can be done kind of locally.
That can be done locally by using just these two equations.
Mm-hmm. Okay.
At the first column, we just need the yellow equation to be correct. At every column after, the only memory we need from the previous stage is the carry value of the immediately previous column,
mm-hmm.
right? Which is why the pink equation has that horse move kind of structure.
Right. Okay.
And that's what the equation also says. The pink equation says that in the ith column, the xi value depends on the xi minus 1 value,
mm-hmm.
right? Yeah. So when we do these automata construction, then the transition relation actually has the information of what xi minus 1 is.
Mm-hmm.
So all of this can be done locally on the comparator, on an automata.
So,
Okay.
Okay, one more comment. Suguman, so this has something to do with periodic numbers and their equality?
Maybe. I mean, I don't understand the connections very carefully, but I feel there is some connection there. There might be some connection, yeah.
They also have this property of normalizing and checking equality of two periodic.
Yeah.
Okay, anyway, that's besides.
I think there is certainly some connection, but I haven't been able to really understand what that is. But I would love to discuss that further. Yeah. All right. Okay. So where were we? Fine. So all right. So the problem was that the xi's can become arbitrarily small for non-integer discount factors. So what we propose is that if we allow approximation, allow some degree of error then we can construct approximate comparators for non-integer discount factors, which are also non-deterministic Buchey automata, right? So to wrap up this part of the story, what we've shown is that when the discount factor is an integer, exact comparators are non-deterministic Buchey automata. For non-integer discount factors, exact comparators are not non-deterministic Buchey automata. We can prove that. So instead, if we allow a small degree of approximation, then the comparators can be made into NBAs. Now, how do we take this comparator and use it to solve the satisficing problem that we had? And here's the intuition. The idea goes back to the fact that the key operation is that of comparison. So the satisficing goal was, given a fixed threshold value t, can we ensure that the cost of every execution exceeds the value t? So all we are asking is whether the discounted sum of a sequence A is greater than or equal to t, where t is the weight sequence of a given execution. Then if the number t is the number small t is represented by the weight sequence capital T, then all I'm asking for is whether the tuple a comma t is accepted by a comparator with the relation with the relation greater than. Now, when the discount factor is an integer, this condition is exactly captured by the exact comparator. And when the discount factor is not an integer, the comparator presents a sufficient condition for the satisficing goal to hold. So what we have been able to do using comparators is take this quantitative goal of ensuring that the cost exceeds the threshold value and reduce it to a qualitative goal of membership of the sequence a comma t in a comparator. And that's exactly how we will design our algorithm. So now for the satisficing goals, instead of optimization-based techniques, we will use a comparator. In the case of integer discount factors, the comparator will exactly solve the problem. In the case of non-integer discount factors, the comparator can be used to generate a sound algorithm. And in fact, that is the guarantee we get. We get that if we combine, what the guarantee we get is that the strategy generated by combining the automata for the temporal goal and the comparator for the satisficing goal will necessarily satisfy both of the goals simultaneously.
Okay.
This algorithm may not be complete because of the error introduced by the comparator in the case of non-integer discount factors. In the case of discount factors, this algorithm is also complete, right? So let's look at complexity. Okay, I lied a little bit earlier. I said that this whole procedure has been completed once we have a comparator. In reality, in order to solve the problem, we need a deterministic comparator. A non-deterministic automata will not work. But it's not a problem because non-deterministic Buchey automatas can be determinized. So we can construct a deterministic form of it and then combine this deterministic comparator with the automata for the temporal goal. The problem is this leads to an exponential blow up in the size of the comparator, and that makes the algorithm extremely non-scalable. Because if you're starting with the comparator with a mu square number of states, the deterministic automata will necessarily have an exponential number of states in the value of mu. So to remedy this, what we observe is that comparators actually have, discounted sum has a very interesting property because of which we can show that comparators, be exact or approximate, are actually safety or co-safety automata. And safety and co-safety automata are very, very specific kinds of Buki automata which are deterministic. And the property, without going into too many details of what safety and co-safety automata is, the property that these automata have is that they really just focus on a finite prefix. And what we observe is that discounted sum also has the same property, that it is sufficient to focus on finite prefixes. The reason is that if you look at what the discounted sum of a sequence is, I can rewrite that as the discounted sum of a finite prefix of length, say I, plus 1 by d power I into the discounted sum of the suffix, here shown by the green and the blue parts. Now observe that as I becomes greater, then the contribution of the blue part converges to 0. So what really matters is the value of the finite prefix. And that is also the key, that is also all that matters for safety and co-safety automata. So we can show that a discount, and then by performing, we have to redo the constructions, but we can show that by using this additional property, that discounted sum only needs to focus on a finite prefix, we can directly construct deterministic comparators. And turns out these deterministic comparators are actually smaller in size than the non-deterministic constructions we had. These comparators only require order mu number of states. And we can further prove that these comparators are in fact minimal. So they cannot be a deterministic comparator with fewer number of states. So by using this additional property of finite prefixes and the fact that safety co-safety automata are meant for finite prefixes, we have much more efficient constructions of comparators for both the exact and the approximate case. So now coming back to the big picture, instead of using the non-deterministic constructions for comparators, we can use a deterministic construction. This deterministic construction is efficient. It only requires order mu number of states. It prevents the exponential blow-up we had earlier. And now we can simply combine the automata for temporal goal with the comparator in order to solve the synthesis problem. As earlier, the problem is, and this is really the first. So this algorithm is not only theoretically sound, it is also scalable, right? So let's talk about how this algorithm performs in practice. We conducted an empirical evaluation over benchmarks obtained from a large series of benchmarks. And just to give you a sense of the difficulty of these benchmarks, the number of states in the graph game ranges up to 70,000 states. So these are fairly large benchmarks. We evaluated on two factors. First is simply evaluating the satisficing problem. So in this case, there were no qualitative objectives. And here we were trying to compare our comparator-based solution for satisficing versus existing optimization-based algorithms for satisficing. And in the second set of benchmarks, we combine qualitative and quantitative goals. In this case, there are no tools to compare against. So we simply evaluated scalability trends for our algorithm. And here we see that the satisficing using comparators solves almost twice as many benchmarks than optimization. In fact, if we zoom into a particular set of scalable benchmarks, then we saw that the comparator-based algorithm actually scales linearly in the number of states in the game. So on this graph, on the x-axis, we have the time taken in log scale, and on the y-axis we have on the x-axis we have number of states in log scale, and on the y-axis we have the time taken in log scale. And because both are in log scale, the slope of the curve indicates the degree of the polynomial. So here we can see the slope for comparator-based algorithm is almost 40, it's at a 45-degree angle, so the slope is about 1, which shows that the comparator-based algorithm actually runs linearly in practice, as opposed to the optimization algorithm, which has a much larger polynomial. I did not get into the complexity theoretic aspects of this, but this is not surprising. The linear algorithm of the linear time algorithm of comparators is also supported by the theoretical complexity analysis of the algorithm. And finally, when we combine qualitative and satisficing goals, we also saw similar linear trends in terms of runtime. But what we also observed is that as the discount factor is made smaller and smaller, the amount taken by, as the discount factor becomes smaller, the amount taken by the time taken grows rather exponentially. And this is because the comparator construction grows significantly as the discount factor becomes smaller in the case of approximate comparators. So to wrap up, in this talk, I introduced comparators. It is really an automata-based method for performing quantitative reasoning. And the key idea behind comparators is that it keeps comparison of values front and center, and it uses that to reduce quantitative problems into qualitative problems. In this work, we focused on the problem of reactive synthesis with quantitative constraints, and we showed that our algorithm is able to give theoretical guarantees of soundness which were not available earlier. Smarter constructions of comparators exploiting properties of discounted sum leads to efficient and scalable algorithms. And another salient feature of the algorithms is that because it reduces quantitative algorithms to qualitative algorithms, one can leverage the progress made in the qualitative space in order to improve the algorithms for quantitative reasoning. In terms of future work, one of the interesting directions, I think, is that so far, our reductions are really automata-based reductions for quantitative reasoning. But we know that in existing work on reactive synthesis, the real improvements for tools and algorithms have come from using constraint solvers to solve the reactive synthesis problem. And so far, we have not used constraint solving, and using that would be a great direction for future work, especially given that comparators inherently have an arithmetic structure when we construct them. It would be interesting to see if constraint solving can be used. It would be interesting to see how constraint solving can be used to solve those kinds of arithmetic constraints which are inherent to the comparator constructions. In terms of theoretical future works, I defined comparators in this work with respect to the discounted sum aggregation function. But in general, one can define a comparator for any aggregation function, right? One could define it for limit average, lim sup, liminf, and so on. So what would be very interesting is to have a principal theoretical, principal theoretical foundations to when an aggregate function would permit a Bucchi comparator and when it wouldn't. For example, we know discounted sum with integer discount factors permits Bucchi comparators, and non-integer discount factors does not. A principal theory behind when this can happen would be very useful, and to simply look beyond Bucchi comparators. Right now, we are relying on the fact that we know how to solve problems with Bucchi automata. But what if some aggregation function could be expressed using a comparator that perhaps requires a push-down element, and so on and so forth. But more broadly speaking, one of the main insights for future work is that if we want to perform quantitative reasoning with formal guarantees, we need to reimagine our algorithms. The algorithms for quantitative reasoning are current existing algorithms really rely on numerical methods, which are not designed for formal reasoning. So what we really need here is to reimagine formal quantitative reasoning with a focus on how could one combine them with richer specifications like qualitative behaviors, and even look for applications of these kinds of things in reinforcement learning, where once again, we are combining quantitative with qualitative constraints, or even arithmetic, where we want to perform arithmetic with formal guarantees. Comparators could be a way around doing that. I would like to thank all of my collaborators. No research happens in isolation, and neither has this. The world of comparators is constantly growing. I would love to collaborate with more people on problems related to formal quantitative reasoning. And with that, I would like to conclude my talk. Thank you for your attention. We can take more questions.
Hi, I have a question.
Yeah, okay.
Hi, Suguman. So do you have, do you know of any sound algorithms in the case of, and for quantitative objectives, and in the case of infinite state systems? I think you're dealing with finite state systems, right? I'd just like to know your thoughts on that. Yeah, thank you.
So for some aggregation functions like lim_sup and lim_inf, which is that for those cases, one can design sound algorithms. But for discounted sum, I'm not aware of algorithms that can soundly solve quantitative reasoning. And about infinite state machines, again, I do not know what the state of the art is with respect to quantitative specifications. But even there, if one can solve the qualitative problem on infinite state machines, then one could imagine solving the quantitative problem using these kinds of technologies.
Thank you.
Yeah, so it's already, there are lots of questions in between. So we could take a couple of more questions and then we stop the recording. And after that, Suguman has said that she will be around for more informal discussion. So we can take a couple of more questions. Anyone?
So Srivatsan, I have a question. Yeah, if nobody else is going to ask. Yeah. Okay, so Suguman, so what about solving the original problem of let's say the optimization problem? Can you tackle that using these techniques? You want to find, let's say, the kind of maybe the highest whatever strategy that gives you the highest let's say battery power at the end of.
Right. I mean, that is a very, very interesting question. So there the comparison is at 2 degrees, right? One is, there the comparison would be sort of, you're comparing, So there are 2 degrees of comparison. And why I say that is because between any 2 sequences, you want to know which one is greater. And then there is the higher degree of comparison that says, I want to find that one sequence which is better than everything else. We did encounter something of that sort in rational verification, where we have a non-deterministic system and we want to know whether, we want to find that one run, which is the optimal for each word. And there we did have to use some degree of complementation, etc., in order to find the optimal value, the run with the optimal solution. So I think there might be a way of solving optimization problem even in this case using comparators, but the algorithm might be extremely inefficient because from what my experience is that to get these optimal values, one needs to use a complementation somewhere. And that can be very expensive. But if you look at the complexity of existing algorithms for optimal solutions, that is much, much smaller. It's actually polynomial in size of the gate. So even if it is possible, comparators might not be the right approach in that case.
Any other questions? So I had a question. Have you considered adding random nodes to the model? Like a stochastic game with quantitative constraints.
Right. I mean, that is actually a very interesting future direction. So, I haven't done that yet, but I feel the problem there is so direct usage of comparators would be a little. So the problem with if you have random moves, what we're trying to optimize is the expected value, right? And in this case, if we think about applying comparators directly, what you will end up with is that you'll end up with expected value of satisfaction of a satisficing goal, which is slightly different from saying that the expected value should be greater than a given value, right? So I feel there is a very interesting question on how to formulate the problem correctly and how to approach it nicely. But even there, the whole idea is that you can take all of these kinds of exciting games, be with stochasticity or multiple agents, and try to apply comparators in those cases. Yeah. But the challenge is getting the right formalism so that you're still solving a problem of interest.
Any other questions? Okay. So it's not, let's thank Suguman once again for the very nice talk, very nice work. So maybe we could unmute and give her a clap.
Thank you for the invitation.
Yeah. Thank you. Okay. So now I'll stop the recording.